This conference will now be recorded.
Guys, any clue? No idea?
Sorry, sir, what was the question?
No, we looked at the virtual warehouses with
Yes.
of the load monitor graph, right? This is
Yes.
one of, so this thing is right.
Yes.
I do have 1 second.
Yes. Some of the load should be one
Yeah,
load parameter.
so that means almost there are no queuing. The
Yeah.
load graphs are very high, and then
Warehouse is fully busy at that time, right?
yes, that is true. I have another. Hold on 1 second. This is the one. Okay. I don't think so. We don't have anything here anyway. So before getting into this one, right? Let's talk about how did we end up? How did Snowflake design this architecture and all this stuff? Okay. So Snowflake, right? Normally, when you look at it, this is the end user. You guys can see my screen, right?
Yes, second.
Yeah. So end user, and then you have this EC2 instance, and then the S3 buckets. So the end user, whenever they run the Snowflake, right, the compute power is EC2 and the storage is S3, okay, which supports auto start and shutdown. So this is what Snowflake auto resume, auto shutdown, right, based on this particular underlying EC2 technology or underlying EC2 service, how it acts. Snowflake is utilizing that and then trying to work on it. Okay, so if you look at this particular thing, right, what are the unique offerings of cloud data storage or the S3 buckets or the cloud storage? Scalability, storage, and compute. So, the important point of it, maintenance completely gone. Sorry, you don't need to work on the maintenance part of it. No indexing, no performance tuning, no partitioning, no physical storage design, tunable paper use. So, scalability you can have on a fly whenever you need. Sorry, guys, 1 second. Sorry. So you can so these are the unique offerings of this S3 buckets technology that Snowflake or AWS offers, or Snowflake which is hosted on AWS or any other cloud blob storage providers offer these kind of features. Okay, and then when you come here, right, there are some challenges with this. Challenges which is the IO latency, because the server farm is somewhere else. You are working on the cloud, and the moment you save a file, it has to go and get saved on the physical server farm. That means the network bandwidth plays an important role here. And so, and the second one is right. Please, can you mute yourself, please, if you're not speaking? Okay. And the second part, CPU overhead. That means depends upon the number of file size that you are trying to save or retrieve and all this stuff. That's all CPU intensive, right? It has to go get your file pretty fast, and it depends upon the CPU. If it's a low end machine, it takes time. High end machine, you get your data pretty fast and all this stuff, right? And the third one is object storage. This is the important part. So in this object storage, right, it's overwrite only. Sorry, it's a typo. You cannot overwrite. You have to every time whenever delete that and then create a new one. So in the blob storage, the feature, one of the major features of blob storage, right, you cannot update the file. You have to create a new file. The old file image, you take that data from the old file, you make your modifications and create another copy. So you cannot overwrite the existing file. So when we talked about micro partitions are all immutable. That means the table will, I'll show you a picture of it and we'll talk about it. So whenever you do an DML activity, the data that is the, so in S3 buckets, right, if you want to modify a file, you have to delete the file and upload a new file which is modified data. That is the biggest challenge with S3 buckets or any blob storages. And then the other advantages of it, right? High availability, durability. We have seen it, right? 99.119 of durability and then 99.99 availability. That means the chance of losing your data is very remote. And the other advantage is, right, you can use what do you call um, the S3 buckets, right? So if you are familiar with Linux, then can we read your data in parts in Linux? Some part of the file from 10th line to 20th line. Can we read that in Linux environment?
Yes, sir.
Or
We can
part?
read.
Yeah, can.
Yeah, we
Yeah,
How
we
can
can
read.
can read.
we how can we read that?
You can specify some line
Line number
number,
we can create, sir.
pixel,
Yeah,
line.
we can create new file and we can
No, I just
uh,
want to read from the same file. I don't want to create a new file from line number 10 to line number 20. Or from,
Yeah,
so anyway, I don't want to get into
we
that. So
can
we
we
can
can
read
utilize
partial.
head and
Yes, yes,
yeah.
yes. We can read partial data from the file. And the same way you can do that in S3 buckets or any blob storages. There are APIs to read partial data from the files. Okay. So these are the challenges where every time whenever you make any modification, it has to be a new file. The old file has to be replaced, and then when the advantages are you can high availability, durability, and then you can read partial data of the file. So if you think what these guys have done is right, they know these challenges and they started utilizing that to their benefit. What they have done, if you look at this data file, or you have a CSV file, which is huge, what they have divided that data file into chunks. Okay, and those chunks they call it as micro partitions. What do they call them as? Micro partitions. And if you look at this, right, they are divided into three parts here. So there might be n number of parts, and then these three chunks are called micro partitions. What they have done is, right, these micro partitions data, whatever that, they are from 50 to 500 MB uncompressed size. Completely compressed size is 16 MB. 16 MB is the size of the micro partition that you can have. And whenever we looked at the unloading exercise, right, when we are trying to unload millions of records, what happened? We see what is the maximum file size that we have recorded. You guys remember that session when we did the unloading part of it and we did 100 million records of unloading. And then with multiple files, when we go and look at the file sizes, right, how much is the file size?
16 MB,
16
sir.
MB.
Yeah,
Maximum we can
so
generate 500,
yes,
5 GB of file.
compress 16 MB. So normally so I don't understand why these types there is in the documentation it says 50 to 500 MB uncompressed, and the max compressed is 16 MB. I don't know if you compress 500 MB, if you do 50% compression also, how much it will take? 250 MB, right? I don't know how
250
they
MB only.
can.
Yeah.
Yeah, they say contradicting statements. I couldn't understand that. But if you're trying to write an exam or speaking to anybody, just go by these words: 50 to 500 MB uncompressed, compressed and zipped is 16 MB max. Okay. So the data that is from one chunk, that is put into one micro partition, and they reorganize the data, whatever the data that is in row and columns, right? They reorganize the data in such a way that data is columnar. And then let me show you. If you look at that, you have order date. The picture might not be very clear. You have order date, title, marketplace, offer price, and currency. So this one chunk of data, what all the, so you have order date one column, right? All the data in one particular column of that particular chunk, they moved into one particular data set. That is called order data. So the columns values are all horizontally placed. The column data that is part of one micropartition chunk, that is horizontally placed. The same with all the columns in that particular micropartition. And after that, they have identified, they have written a header here for this particular. So whenever you ingest some data, it looks at the data part of it and then organizes the data. It is divided into multiple chunks of 50 to 500 MB uncompressed or 16 MB compressed data. What they do, they go and write in the files. The max micropartition sizes. So the file might be of huge size. We don't know. Each table will have a file, and it can be multiple files. They have a different versions of files. So these micro partition data is written into a file, and the size is 16 MB compressed. So the zipped file is part of the, that means the entire file is compressed, and the data that, so you go and then write the data into the file in this particular format with header and then all the columns, and they put it as micro partition. That means in a file, they know where the micro partition starts, where the micro partition ends, the details about the micro partition. And then they have a header. And in the header, they have total number of columns, total number of distinct values, total number of null values, and what is the min value of a particular column, max value of a particular column. These are the the features that they store in the header. If you look at the header, right? So order date, what is the min value, max value, title, min value, max value, and it gathers all the details of all the columns and then stores in header. And how many nulls do we have in order date? How many distinct values do we have in order date? So it reads the metadata and stores in the header. So, and this information is written in a file, and those files are compressed, but the data that is written part of a micro partition which is compressed will be 16 MB max. And then they know the starting of ending of the micro partition. So and then whenever, this is whenever you query the table, right? What happens? They know which particular column that you have queried and what are the very conditions that you have given. And this metadata header information metadata is stored in the global services metadata layer. All the micro partitions header data is stored in the metadata layer. The moment you issue a query, it goes and looks at the metadata layer and then sees what are all the micro partitions that this data is in, because they know the min and max. So whenever you have given the condition, you have given an equality condition or between condition, it identifies it. They have an algorithm to identify what are the micro partitions. And then it goes and reads from the S3 buckets that particular data partially from the file to get you the data. Are we clear? We are talking about behind the scene how things work
Sir,
and how data gets stored in the Snowflake.
sir, one micro partition can have any number of columns, right? It's not one
Yes.
column.
No, no, n number of if you so normally what happens, right? It goes and fits in all the columns in one single micro partition. So if we were trying to load JSON, right? One entire row, what is the max size that the entire JSON row can fit into?
16 MB.
Yeah, why did they use 16 MB? Because they want to cram the entire record into one particular micro partition. So that is their limitation. The same way, all the columns are fitted into one particular micro partition. So if you increase the number of columns, the number of rows that they get stored in the micro partition will be less because you have more number of columns to be accommodated in micro partition. Are
Yeah,
you able to follow me?
yeah. Number of columns is inversely proportional to the number of rows it stores.
Yeah. The more number of columns, the less number of data that gets stored in the micro partition
Okay.
because the limitation is only 16 MB. And guys, there is no clear cut definition of how this is all my personal experience. I have researched, basically I studied too many blogs, I looked at the documentation. This is my personal, there might be a mistake as well, but I am 99% perfect correct with my experience, and I love what happens behind the scenarios. I'm more passionate about it. I experimented, I researched, I studied, I put in a lot of time to get you the data, get you this information. You cannot go and get this information in any Snowflake documentation anywhere. Okay. So they don't, Snowflake doesn't provide more details of how things work in the background. Maybe in the coming days they might, because it's all proprietary for them, right? They don't expose all this stuff. So how blob storage gets stored. So this is a combination of how S3 or blob storages work. Whenever you read, how do they read them? So bits and pieces of information from different technologies, I correlated and I'm presenting it to you. Okay. So why do they read partial data? Because the micro partition data is sitting in a file and the file is compressed, and this compressed part of the data micro partition is part of a file, and it knows all 16 MB compressed data is written in one particular location. It can read, even if you have zip the entire file, it can read partially from the zip file. And then whenever you issue a query, it knows what micro partition that your data is lying into. It goes and reads, but because the header information is stored in the metadata, it has all the information about all the columns of that particular micro partition. If your query result has to be read from the micro partition, it goes and reads the data from the micro partition. And if you have in your query from this table, if you have select order date and title from order information table, it goes and selects only these two columns, and you are saving the selection of these three columns. When you say star, right, it has to get all of them. So star is an expensive thing in Snowflake. Don't use star because it has to go and read all the data from that particular micro partition. If you give them the column names, it's much more performance oriented. It goes and gets only those two columns because it's IO, right? You're reading from the S3 bucket, getting it, and your compute, how much compute power you're spending depends upon what are you trying to read from the buckets, right? If you're trying to fetch too much data, you need more power. So star is are not advisable. You understood, right? When you say select order data and title, it goes and from the micro partition, it partially reads the order data and title of that particular micro partition. When you say star, what should it do? It has to read order, title, marketplace, offer price, currency, everything he has to read. We really don't care about it. We'll just use star and limit, and then we do. But you can understand how things work behind, right?
Yes, Shekhar.
Okay. So coming back, now the data is, so if you issue a query, oops, 1 second, guys. I cannot. So you have order data, and then you issue a query. Where is this? So select offer price currency from orders where marketplace includes so and so. So it has to read. So first first thing, right? You have given the condition where marketplace is Amazon. So it goes and looks from the column marketplace, from the metadata, where this amazon.co.uk, what is the min value, max value, what is the range in which these micro partitions lie. First thing, it goes and checks what are the micro partitions that doesn't have this particular range, and it omits them. The first thing that it has to see what micro partition it has to scan, what micro partition it doesn't need. First it goes and scans which micro partition that doesn't need it for omission purposes. So it identifies what are the micro partition that doesn't have this particular data. So to reiterate in a SQL terminology for you to make to understand, if this metadata is stored in a table, then what would Snowflake do? Goes and queries, select star from this particular table where it has all the micro partition metadata, where the marketplace is not having amazon.co.uk. Get me all the micro partitions which doesn't have this particular data. That means I don't need to scan all of them. Okay, it gets the data. It omits all this micro partition. Then when you omit the micro partition, the other remaining partitions are for scanning purposes. It goes and queries, what do you have this one? So the first part of scanning the micro partitions which are not needed is called data pruning. Pruning means, pruning a tree means you're cutting a stem from a tree. Normally pruning happens with roses. If that particular thing is not properly there, you prune, or prune a flower. The definition, English definition of prune is cutting. The first part, what is this, an important data interview question. People ask, what is data pruning? Data pruning is a way that from your micro partitions identify which micro partition you don't need. Okay, and then it identifies which it needs, and then it scans and gets you the data. Are you able to follow me?
Yeah.
It goes and
Yes.
identified this particular thing is in this particular micro partition, and out of this it has to read 2 columns only, and then it goes and reads the 2 columns and get you the data.
Sir, sir, that information it will get from metadata only, right?
Yes.
Okay.
Okay, so now you understood, whenever you run a query, right, what happens? It goes and looks in the metadata. It has all the details about what micropartition. It does the pruning part of it. That means it goes and identifies which particular micropartitions are not needed, and it omits them. And then it identifies which particular micropartitions are needed, and then which particular micropartitions are not needed, sorry, which are needed. It goes and then scans them, and it knows which micropartition to scan, because so based on the min and max values. It has all the details about that particular micropartition data. So it identifies and then reads that particular data, which particular column that you want, and gets the data for you. It filters the data based on the condition and all this stuff. Okay. So now you understood pruning, right? What is data pruning? Omitting the number of micropartitions that are not needed for your query is called data pruning. Okay. And coming to database storage. So this is what the moment when you try to insert some data, right? The moment you insert the data is reorganized again in the micropartition. The micropartition gets changed all the time whenever you do insert or update or delete. The data gets organized on the fly. This is the fundamental difference between Snowflake and then Redshift. I'll tell you that is a very big minus point for Redshift. This is where Snowflake gained some brownie points. So whenever you're trying to data is reorganized upon ingestion and stored in proprietary optimized compressed and columnar format. You have seen, right? There are people in interviews, they have asked, they have given the table, and then can you explain me how the data gets stored in micro partition? So that is the reason I'm being very specific. The data gets horizontally placed. The column data, if you have 5 records, that will be placed horizontally in micro partition. You guys are able to follow me, right? If you have department number and if you have multi-million records, so 2 million on an average, 2 million records can be cramped into one 16 MB compressed file. Are you able to follow me?
Yes.
So 2 million records means huge data set, right? So whenever you update something or delete something, this particular micro partition, it has to create a new micro partition. This happens. And then whenever at the time of ingestion, right, it goes and reorders and then it creates new, it takes the old data, gets the new data, appends it on the fly, it does that and stores. And everything happens in nanoseconds or seconds. And whenever you observe something in Snowflake, right, reading data is very, very fast. When you try to do insert, update, delete, it takes time. You observe that when you're especially when we're trying to do lot of data, it takes a lot of time. So DML, it has to recreate that the entire stuff and recreate the micro partitions and then delete, ignore the old one and create a new one. So it takes time. Okay. And the data that's stored in a columnar and they call it as FDNs. There is some French name for this particular thing where they store it, the micro partition. FDN means there is a French name. If you Google it, you will get to know. So these micro partitions are not visible or accessible to anybody, even though these micro partitions are part of S3 buckets and they cannot be accessed directly. Only a Snowflake user can access it using SQL query. Even Snowflake cannot read this data because it's completely encrypted. Only the SQL query. And Snowflake manages all aspects of data storage, organization, how, what kind of file and all this stuff, file size, structure, compression, metadata, statistics, etc. Optimize compressed columnar format. Okay. And table and micro partition metadata. How does it store in the header table? It stores the entire row count, table size, file references, and table versions. If you look at it, right, table. So how many files it has for a particular table? The data, how in how many files this particular data is residing? What is the table size, the total size in bytes, and total number of counts? These data will be there in the metadata as well. Snowflake automatically collects and maintains metadata about tables and their underlying micropartitions. And if you say micropartition column level, range of values, min and max, number of distinct values, min max values, null count. When you have the range, right, then you can issue a query to identify which particular micro partition has this particular where condition filter that you are trying to do. But that's not those so simple. You have many conditions, huge sequels, joining 10 tables on different columns and filtering that has to be done on the fly, right? But it has all the data. So in Snowflake, the data, the reason for having no indexes, no partitioning, nothing is because it stores data in chunks. They are called as micro partitions. It's all compressed data. The moment you issue a query, if you have millions of records, it goes and scans and identifies what partition that it doesn't need, and then it identifies what partitions it needs, and then scans them, gets you the data. Okay. And because of this data is you're reading from metadata, you don't need to use a virtual warehouse, user created virtual warehouse to run, to utilize when you're trying to query from data. Like if you look at it, right, select min of max of, then it goes and gets the metadata because it knows what is the min and max of the entire table, right? It reads from the metadata itself and gets you the data. It doesn't even query the table. Snowflake's metadata allows some queries to be serviced as metadata only operations, no compute required. Are you able to follow me? Okay. So then, yeah. So, and what kind of metadata? Where is it stored? First part, statistical metadata stored in global services layer. The metadata that we are talking about, the row level, table level, all this data is stored in the metadata layer. And you have the table related files, what kind of files, what is the size of the file, where is it stored. This is stored in they use another open source database called foundation db. FDB is foundation db. Foundation db is very fast in getting, it's open source, you can also use it for any other purposes. So they use foundation db to retrieve the data and all this stuff. So in that foundation db they store references to physical file objects in cloud source. Which particular table has which particular files? You have to have a relation, right? You have thousands of files, and then which table is pointing to which kind of file. So they establish a relation between a physical and logical. Table is a logical structure. Select start from EMP, then it goes and see this particular EMP table has what, how many number of files, and then it reads the data from it. Table versions, so it has different table versions. For example, if you have a time travel of 1 day and your files have many number of files, you have different file versions, right? So which particular files it has to read from this particular so that to get the time travel part of it. The more your data retention period in days, the more charges will be paid because it has to store too many files. In this particular data, it stores what are all the tables, what are all the files, what are the versions of the files, so that whenever you are trying to do a time travel, it goes and identifies which particular file it has to check. Are we clear? Okay. Let's go and look at what the characteristics of micropartition. All data in Snowflake tables are automatically divided into micropartition, which are contiguous units of storage. So normally, whenever you do, right, whenever you ingest, whenever you do a DML, it goes and sorts and organizes the data. So it identifies a particular column. Mostly, it goes and looks for a if you have any date columns in your table, right? It goes and picks that particular date columns, and if you have any regions where like North America, South America, if you're organizing. So it identifies the columns based on the column names and then organizes the data in Snowflake. So something like if you have in an employee table, you have hide date, right? Whenever it stores the data, it goes and organizes by hide date. Min of hide date, max of hide date. It automatically sorts and inserts. Whenever you do, right? Whenever you insert or update or delete, the micro partitions change based on the data ingestion. It reorganizes the data and stores. So in Redshift, right, this reorganization of data doesn't happen. They employ a job at the end of the day or sometime, they, I don't know the frequency, they go and then vacuum the data. That means they call it as vacuum. They go and reorganize the data, especially to reset the data on the flight. They don't it, they just keep on dumping into wherever the data. And if you have too much DML activity on or at the end of the day, they go and then reorganize the data so that the performance will be fast. And the reorganizing the data costs you, and you cannot do any DML activity while the vacuuming is happening. And the vacuuming time depends upon the size of your table. The huge table, lot of time for the vacuuming, and you have to pay for it whenever it reorganizes. So here in Snowflake, it does them on the fly. The moment you give an update, the moment you give an insert, it goes and reorganizes the data and then stores. And it identifies a pattern. It goes and looks for the hide date or any regions or something, and then it automatically sorts the data and stores it into micro partitions. Okay.
For Snowflake also, we are paying for that, for reshuffling and all.
No, we don't do. Yeah, that definitely. But there is no vacuuming, right? The moment you do an insert statement on the fly, it does the reorganization.
Yeah, but some compute power is required to do that, right?
Definitely, you have to pay for it. Without, so that is the technology, right? That's why we are using it.
Okay,
You have
but they're
millions of
doing it.
records and
Okay, they're doing it in the back end, right? So it's not transparent to us.
yeah, it definitely uses your compute power.
Yeah.
But they do
Um,
on the fly in the most optimized and the best way so that you minimize your compute power.
but they don't use the custom warehouse for that one, right?
No, they use custom warehouse.
Oh, custom warehouse only. Okay.
Yeah, because they're working on your data, right? It's not
Okay.
metadata. They're working on your data.
Okay. Okay. Okay.
So Snowflake uses columnar scanning of partition so that the entire partition is not scanned. If a query only filters by one column, so it doesn't need to scan. I have given you, right? If you're trying to filter on a one particular column, it goes and looks on that particular column, and you have given something like where department number is equal to 10, and it has micro partitions. It goes and looks the micro partitions which doesn't have department 10, it omits them. Then it identifies the micro partition which has department number 10, and then it goes that, and you have given select star from EMP, then it has to get all the data from the micro partitions and gets you the data. How does it give 10? Because in the micro partition you might have, whenever it's stored, right, it will have in the column 10, 20, 30, whatever the, so it has the range. What is the min range? Min range is 10, max range is 20, and then it goes and identifies by the range and gets you the data. I'll show you an example as well. Okay. And then a query that specifies a filter predicate and a range of values that access 10% of values in the range should ideally only scan 10% of micropartitions. This is an important thing for your tuning purposes, guys. Whenever you're trying to tune your query, this is the one of the rule that I follow, and I would suggest you to keep in mind. If somebody asks you, right, how can you tell that your query is doing good or bad? Then if your data is so the query, the data that after issuing the query, it's getting 10% of your data. For example, you have about 100 rows and your query returns only 10 rows. Then it should scan 10% of micro partitions. Total micro partitions, if you have, then we are talking very unhypothetically. So this particular thing happens only when you have, if you have 100 micro partitions and your query returns about 10,000 records, and then it has to scan only 10% of the total micro partitions. Meaning it has to scan only 10%, 10 micro partitions. So whenever you are issuing a query, the amount of data that you are retrieving is directly proportional to the percentage of micro partition that you are scanning. If you are retrieving 2%, then you have to scan only 2% of the total micro partitions. If you are retrieving 10%, you have to scan 10% of your micro partitions. That is the thumb rule you have to remember. Are you clear, guys?
Yes, sir.
Okay. So this is pretty much about there is some more information that, so snowflake does not prune micropartitions based on a predicate with the subquery, even if subquery results in a constant. Okay, the biggest problem is, right, whenever you write subqueries, it cannot prune. That means it cannot allow, it cannot, what do you call it, identify the micropartition that it doesn't need. So that snowflake does not prune micropartitions based on predicate with a subquery. That means if you have written some value in a subquery and then filtering the data, right, it cannot prune the micropartitions properly. So subqueries are very bad in snowflake. When you are trying to tune your SQLs, make sure you avoid subqueries. If you can join them as an alternative way, that's much more faster. Don't use subqueries in snowflake, because when you try to filter some data in the subquery part of it, right, even though if it's a constant, where select star from emp where department number in, select star from, or you can say select 10 from dual, or you can filter the department number equal to 10 hard coded constant. If you write something like this, right, snowflake cannot properly prune means cannot properly omit the, it has to scan more number of partitions to identify what is needed, what is not needed. It will spend more time and the performance is bad. Are we clear, guys? So this is what, and clustering, this is what I was talking about, right? Data stored in tables is sorted, ordered along natural dimensions, date and geographic regions. This clustering is a key factor in queries because table data that is not sorted or is partially sorted may impact query performance, particularly on large tables. So if the data is not sorted, right, so the moment you sort, it goes and then organizes the micro partitions in such a way that they are contiguous. Contiguous means one after the other in a serial line. So it knows, it has a pattern to identify the data, and it reads from the header, it goes and reads the data. So the way that the micro partitions are organized, the columns or the micro partitions, it becomes easy for snowflake to retrieve your data. And this particular phenomenon is called natural clustering. What do you call this as? You are not telling on which particular columns you have to organize and all this stuff. Snowflake automatically reads dates or data and all this stuff and then identifies. That is called natural clustering. The moment you keep on inserting data, it's automatically organized and then stored in a way, in a natural way, so that it's all orderly organized, so that whenever you query, you get the data fast. This phenomena is called natural clustering. Okay. So whenever you issue a query, right, these are the data. So this is the micro partition. You see this data, product, customer, amount, date. So it's all sorted by dates, organized by days. February 14, 15, 16, and the other data is sorted accordingly. And whenever you query, it goes and sees total micro partitions scanned 13, partitions total 73. That means if so, how much is 13 out of 73? How much is the percent?
20, sir, almost.
Yeah,
Almost
that
20.
means you are trying to get 20% of the data from your query. You are querying 20% of data using your query. Then the snowflake has to scan 20% of your micro partition. So that is the reason it scanned 13. So these are the thumb rules that you have to remember, so that whenever you're tuning your sequence, right, these things will come into handy. Okay, we'll look into the profiling part of it. We'll come back to that. This is what is called clustering. So this is natural clustering. So what is the advantage of clustering? Unnecessary scanning of microprotection during querying. That means it knows the data is orderly organized, and the moment the metadata is also organized, it goes. The reason is, right, in your file, when it stores, when you're trying to read from part of the file, it knows the data is organized, it goes and reads. So if you have data in 10 different files in 10 different locations, right, and that is not ordered, so then it becomes difficult for snowflake to read that. So then if its data is ordered, means you have the same set of data in the same file, and then you can pull it from one file rather than pulling from 10 different files, because the data is organized and contiguous. When you're trying to pull the data, whatever the query that you have given, you might read it from 2 or 3 different files, because that same data set is lying in this contiguous files. And again, it depends upon the complex query that you write and all this stuff. That's a different story, but basic foundation is this particular thing. First, prune micro partitions that are not needed for the query, then prune by column within the remaining micro partitions. And once it does, and then when you come to identify these micro partitions that you need, right, then prune by column. That means check which particular columns you don't need and omit them. It looks at the total number of micro partitions that comprise the table, the number of micro partitions containing values that overlap with each of them. So there is another thing called overlap. That means, for example, department number 10, and if you have huge data with department number 10, and department number 10 can be in multiple micro partitions. For example, if you look at this data, right, 11/12, and for this 11/12 data, you have more data in it, so it has to pump it into multiple micro partitions. See, 11/12, 11/12, 11/12, 11/12. So that is called overlapping of data. When you have issued a query on the date, right, how many micro partitions it has scanned now, where date is equal to 11/12? By looking at this, can you tell me, guys, please? Select star from this particular table, table T1, where date is equal to 11/2. How many micro partitions it has to read to get you the data?
3 micro partition.
Why 3?
Micro partition 1 is there and micro partition 2 also is there,
Yeah.
and 3
So the 11/2 is residing in partition 1, partition
and
2, partition 3. but you have some overlap. So this is entirely only 11/2, and here if you look at it, right, 11/2, 11/3, and then here also 11/4, and this one has different. So when it's organized, right, the dates are organized, and then it has overlaps as well. So so it has to first fetch which are not needed, then fetches which are needed, and then it goes and prunes which columns it doesn't need, and then based on the filter condition means it has to scan these three micro partitions. Okay, this is the way that Snowflake normally gets it, and it has other two. There are some other things called cluster depth. Okay, so if you want to look at how the data is organized in your Snowflake, how the natural clustering is done, and whether the data that is sitting in your Snowflake table is of good health, you can look at the cluster depth and then identify the data. So clustering depth tells you the overlapping of the data. So whenever you're trying to do too many DML statements, right, then the data, even though it's all organized, right, over a period of time, it deteriorates. It has to scan too many files, too many partitions to get your data. Okay, so if you look at the clustering depth of a table, then it will tell you the health of whether it's properly organized or not. So if you look at it here, right, you have a table, and the table has a column called names, and in the first part, right, it has about 5 micro partitions, 1 2 3 4 5. And whenever you go and say in the top level thing, select star from table where name is equal to shaker, how many micro partitions it has to scan?
All five it has to scan.
Yeah, reason, all 5 of them are overlapping, right? So the overlapping micro partitions are 5, and the clustering depth is also 5. That's called the clustering depth. Depth means the number of micro partitions it has to scan to get you the data. And you have a lot of overlapping. When we talk about thousands of records, right, then you definitely have overlapping, and then it has to scan. So if this one is not a good candidate, you're having higher the depth, it's not a good candidate. Okay, and in the next scenario, when I say select star from this table where name is equal to shaker, how many micro partitions it has to scan?
3.
Yes, so
Last
that
3.
is
K
the,
to Z.
because you have 3 overlapping micro partitions and you are having 3, that is the depth. Okay, and then let's get into the second one, the next one. If I want to query from this one, right, how many overlapping partitions are there in this entire? You have 3 overlapping partitions. And if you say select star from this table where name is equal to shaker, how many partitions that it has to scan?
Again 3, sir.
How is it 3? So
Last one or last but one here? Sorry.
no,
Last
this
but
one. Yes,
one.
this one. When you say
So
select star from this table where name equal to shaker, how many micro partitions it has to scan?
yeah, middle one only. Only middle one. Out of
Middle one means you tell
L,
me the
L,
ranges.
L to S.
And how about
L,
Q to
and
Z?
Q to Z also. Q to Z also. Yeah, 2.
So now you are able to understand the range, right? It micro partition automatically stores the ranges, and it identifies the ranges. It becomes easy for Snowflake to query between a range. So it has the min and max values, and then it queries the range of values. It starts with A, ends with this one. So it can easily, the algorithm that you use in your mind, they have applied onto the snowflake. Are we clear?
Yes.
Yes.
So it has to scan only two. But how many overlappings are there? There are three partitions which has overlapping, because the data L is in K, between K and N, and L and S. So there are some three overlapping, but the depth means how many partitions it has to scan to get you the data. That is called clustering depth. And if you have data like this in the bottom one, and name is equal to Shaker, how many partitions it has to scan?
Only one.
And there is no overlapping, only one. Meaning, the lower the depth, the better the data is organized. Are we clear?
Yes, sir.
Yes.
So where do we know that depth information, sir? Oh, okay, we have the query,
There
right?
is a function. That's what I'm talking. System dot dollar clustering depth. You query the table and pass whatever the columns are tables. It gives you the clustering depth. Okay. So there are two things. One is two functions. One is clustering depth and clustering information. So clustering information gives you lot more data. Clustering depth gives you only the data and the depth of that particular table. Let's do that. Let's query that and then see. Okay.
Shikhar sir,
Mm-hmm.
the example what you have given is with respect to character set. What if it is numbers
Doesn't
and numbers
matter.
range
Num,
can
num, yes, range. It's
number
much more
range
easy.
can
Yeah,
yeah actually yeah how
number is
that
much
will
more.
be chunked yeah here
Number is
we
much.
have sorry sir
Go ahead.
sorry yeah
Go
let
ahead. Go
me
ahead. Go
finish
ahead.
yeah
Finish your question. I can answer that.
yeah yeah because the number can varies from 100 digits or 10 digits or 20 digits here we hardly have 27 character 26 characters who can identify the depth when the number ranges from different to different sizes then how does that be identified.
They get started first and then loaded into the micro partitions. If you have 2 million records, each record of this much bytes length can be cramped into one particular micro partition. When you're talking about 2 million records of each this much size, then how many numbers can you fit into that? Does it really matter?
Okay. So actually, what my understanding was like it creates a ranges like A to C, B to M, and C to Z sort of ranges, and it identifies the particular letter falls in which range. Am I right, sir?
That is the algorithm that we do it, and the same algorithm applies for the numbers as well, right?
Okay. So it checks for 1 to 20, 20 to 100, and 100 to 200. In that way,
Yeah,
similar way.
it doesn't need to be 1 to 20. Whatever the data that you have inserted into the table, if you take
No, no,
employee
I'm
table,
just taking one example. Example,
yes,
taking
yes,
one
yes,
example.
yeah, I'm coming
Okay,
there only. So if you say
okay.
select star from EMP and then employee number, what am I looking at? This admin only, right? Security admin. I'm gonna change it to sysadmin. So you have employee number, right? Order by EMP-NO. This is what, this is how it stores the data in a micropartition. It orders them. You have the min and max range. Now what can you do? You have duplicate records also here, but anyway. So it goes and orders and then inserts the data into the table. Right? So the min and max of all this employee number, everything comes into picture when you talk about it. So if you go and look at the history query, right? Select star from EMP and profile. So table scan EMP, partition scan 4. Okay. We said select star, right? Star means it might get 200 records or 100 records. I don't remember the exact star thing. And then I ordered EMP-NO, order by EMP-NO, null slash, and then it fetches the entire data. So this is what it is. So let's go and then look at Snowflake sample data. We have SFTC 100, right? We have store cells. Store
So
cells
this
which are the,
clustering part is a default nature, or we ourselves
yes,
can
no,
build.
you don't do anything. It's a natural clustering, I told you, right? That's naturally happens.
And is there a feasibility to man by enforcing some based on some columns?
Yes, we can do that. That is called clustering keys. I will talk about it.
Okay.
Guys, I'm sipping my tea as well. You might see hear some noise. Don't worry, please. Okay, select star from this table. I'm saying limit 10. So it has to get all the columns on the micro partitions and get only 10 rows. So this is, I'm using this particular thing. Oh, hold on. So if you go and look at this particular history, right? This is the query. What is happening? Is it not? Table scan 93%. Okay. So how many partitions are here? 721k partitions, and we just randomly 10, right? So it just, this is the partition pruning part of it. It scanned only one partition out of this particular things, and then we got the data. Okay. Now I'm gonna go and then where okay, select star from this one where sold date sk is equal to so and so. I'm just running this query. It takes almost 55 seconds or 1 minute. I'm not sure, but it gets too much of data. Let's see. See, 52 seconds. How much data that it has fetched? Ones, tens, hundreds, thousands, 10,000, 100,000, millions, 10 millions. Okay, 86 million. So if you look at this, right, how many rows do you have? 288 billion. Ones, tens, hundreds, thousands, 10,000, 100 millions, and so 288 billion, and then it fetched 86 million. Let's go to the history part of it and refresh. So table scan 19%. So 721, 766. So this is the number of partitions it has scanned to get you the data. Okay, and then it filtered it based on the condition, and then this is the final output. Got it? So this is how it works, and then select system dollar clustering depth.
The number of partitions equal to the total space occupied divided by 16 MB. Na?
Yeah, that is compressed.
Compressed one. Yeah. But whatever the figure we are getting there, that is based on that calculation only, right? So they do the partition based on compression only, right?
Yeah, because normally 721, 766 is your total number of partitions.
Yeah.
Calculator. So into 2 million records, 1,000, 20,000, 200,000, 2 million, right? One cents, hundreds, thousand, 10,000, 100,000, million, 10 millions, 100 millions, billion, 10 billion, 100 billion. So it should be somewhere 288 billion is the one that they have given, right? So that means
Yeah.
they did not put 2 million exactly in this one. They might have used
Of course, that depends on the number of columns, right?
columns, the size of
Yeah.
the columns, data types of the columns, and whether it's dates, timestamps, and a number, and the size of the data that you have ingested into the table. So there are many parameters to identify the row length.
Yeah. No, if you convert the TB into MBs, then 10.9 TB is there, right? 10.9 into TB in MBs divided by 16.
Yes, that is true.
Yeah.
If you go and look at this particular table, store sales, you have 10.9 terabytes.
9 TB, yeah.
So that means divided by 16 MB will give you how many number of partitions that you can have.
Yeah.
Okay, so let's go and then run this.
Shekhar sir, which data type would lead poor performance in terms of creating these partitions?
No, there is no as such. The snowflake
Okay.
especially is very good dates and timestamps, much better than strings. There is a difference, but we cannot say poor. They
Okay.
work very good with dates and times rather than with strings. That's what they say. Because the data is organized by the dates normally. So it's much more easier for them to bring. So
Yes.
that's how they've done.
Okay. So organization it makes easier when compared with numbers and date. So it
Yes,
is easy for to fetch the partitions easily. Okay,
yes,
got it.
yes, yes. I'm just trying to see if there is some issue with where it's being said. So for example, data TBCDS 100 invalid identifier. We have to give in quotes. And the clustering depth is 2.749. Okay. So meaning on an average, your data has how many overlaps here? 2.74 partitions of overlap you have. So if you look at this particular diagram, right? So if it's 3 means 2. So your data is falling between 2.74 means you have this many number of overlapping partitions, right? Almost your data, whenever you scan your data, it has to scan 2.74 partitions to get your data. That is the depth. So if you look at here, right? What's up? Whenever you query, if you have data like this, it has to scan only one partition. The depth is 1, and that means it has scan. If you here it has scan 2 partitions to get your data, and here it has scan 3 partitions. In our scenario, it's 2.74. That means at a given point of time, it has to scan 2.74 partitions to get your data, right? That's what the clustering depth is. And then we have another thing called clustering information. So clustering information gives a lot of details about store sales. The queries process or not. If you get the results, then you'll get to know, right? Whether no, Narendra, I did not get you the question properly. Can you repeat that again? Okay. No, how do you identify whether a query is processed properly or not? That means whether it has run in a optimal way or not. Am I correct? You have to look at, it's a very generic thing if that is the case, right? So you have to look at all the parameters, look at the number of partitions that is scanning, total number of data that is getting, and then look at when you're trying to insert, whether it's a DML activity or just a query. So you have to look at the query and then look at the response time is basically the important one. If the response time is good, you don't normally go and dig deep into it. If the response time is bad, then you deep. So you have to look at the load monitor graph and see how much, how is the load on your compute warehouse. If it's heavily loaded, if it's going to queue, it will take a lot of time. So there are many parameters that you have to think through. And if you look at this, right here, clustering by keys, these are the 2 keys that they have been clustered by. We'll talk about it. And then total partition count, this much. No problem. And total constant partition count. So whenever you reorganize the data, some of the partitions, they have the same set of data. That means we looked at, there is an example here. If you look at this, right, this 2 2 2 2 2 11 12, you might end up with some partitions that they have similar set of data, even though if you have reclustered, modified n number of times, that is the best optimal thing that can fit into your micro partition, right? That is called constant micro partition. If you look at this, right, you have different sets of data, 3 4, this one, this 5 and all this, but this particular micro partition, there's 2 2 2 2 2 and then 11 2 11 2, and then name and country might be the same one. Even if you reorganize many number of times, it, if this particular constant micro partition cannot be changed, because even though you organize, it comes and sits in the same way. Whenever you organize your data ordered by this particular thing, right, there might be some micro partition which will have the same set of data in all of them, which cannot be, even if you are reorganized n number of times, that comes and sits in the natural way. That particular thing is called constant micro partition. Okay, there are about 10 constant micro partitions. Average overlaps 3.483. The overlaps is 3.483. Average depth 2.7495. Based on your query, the depth is overlapping means if the data is in multiple partitions, that is called the overlap. And then at a depth of 0, there are no records. That means all partitions have overlapping. At depth of 1, that means there are partitions which had overlap. There is only two partitions which had overlaps. And at a depth of 2, that means the, what do you call it, whenever you query, it has to go and scan two partitions to get your data. Or let's go by so the data is overlapped between 3.4 partitions, but whenever you query, right, it will go and then has to scan at a depth of 2. It has to scan this many number of partitions to get your data. At a depth of 3, it has to scan 3 partitions, this many number of partitions. Out of the 721, at a depth of 2, you have 180k partitions. At a depth of 3, you have 540 partitions. So what is the depth? Given a query, how many partitions it has to scan? Based on the query that you have given, so it has to scan, if at a depth of 2, we have given a condition where it has to scan, then it has to scan this many number of partitions to get you the data. So this information gives you what is the histogram means, at what particular depth your data is. By looking at it, if you have at a depth of the lower end, right, that means the data is not organized properly. It has to scan 16. At a depth of 16 means it has to scan 16 partitions to get you this particular depth. Means more the depth, the so we even looked at it, right? So if you get a query and then the query has more depth, then what does it mean? More depth means, what does it mean? The query needs to be tuned. The data is not organized properly. It needs to be tuned. When you look at the depth, and the depth is, so this is much more better. You have your partitions organized in a better way. The depth is less. If your depth is 16 or something, then in the histogram, then the data is not organized properly. More the depth, the number of partitions in more the depth, then the data is not properly organized. Are we clear? Okay. And then, so what is
Shikhar
the
sir, for curiosity, can you please go to the file, I mean, Node++, yeah. For curiosity, what best we can get the shortest depth, or like 001 is there, or 002. If you consider in this case, what best could have been done to get the best performance or least depth?
There are two things. Here we are looking at how your the data is stored in your micro partitions. So when that means there is not much of DML activity happen. Whenever you have the data is properly organized based on the data that you have. We have 280 records and the data is properly organized by these dates, and then whenever you query, it can get you the best. And when you do too much of DML activity on this particular table, in a real-time scenario, the depth goes down. That means the partitions, micro partitions, whenever it reorganizes the data, right? It keeps on pushing. Too much of overlapping happens, and it has to scan many partitions to get your data. So that's what happens. So this gives you the histogram tells you how your data is organized in your micro partitions.
Okay.
So
So,
based on
and
this, yeah.
explicitly, we don't have much control on it, right, sir?
No. You can do can control it. I'll tell you how can that can be controlled,
Okay.
but it's gonna cost you.
Okay. Okay.
Okay. So what is the clustering key?
Sir,
Clustering
micro
key
partitions
is
are not constant, right? They keep on changing, right? The data internally.
the moment if you do on DML activity, they keep on changing. But the micro partition is immutable. That means once a micro partition is created, you cannot modify the micro partition. You have to create a new micro partition with the same set of data and
No,
all
what,
this.
no, what does it mean again? No, we are saying that internally data reorganizes every time, but you
Yes.
are saying it is
And
not
no,
immutable.
no, no, no. It creates a new micropartition. The name of the micropartition gets changed. If your data in the old micropartition is MP1, whenever you reorganize, it creates MP2. MP1 is gone. That is there for your time travel purposes.
Okay. Okay. If time travel is not there, then
It just deletes MP1 and then it creates MP2. That's it.
oh, okay. That means we cannot modify the micro partition. We
Micropartition. That
can.
is the blob storage. That is the fundamental aspect of blob storage. You cannot modify a file. You have to recreate a file or you have to have a new file with the same modified data set.
Okay.
Okay. So what is a clustering key? Clustering key is a subset of columns in a table. Column are expression of a table that are explicitly designed to co-locate the data in the table in the same micropartitions. That means this clustering key helps you to identify the data, co-locate the data in the micropartition. When you're trying to create so there are two ways of doing it. So the first thing is right natural way of whenever you're trying to insert you it automatically starts in a natural, that is called natural clustering. And then if you think that your clustering is not good, that means the queries that are running on the table are not performing well, they're taking a lot of time, then you can go ahead and create cluster. You can create a cluster on a table. Cluster is something like to correlate cluster, right? You can say like creating an index on a table. When you create an index on the table, so what happens? The data is all the keys are stored separately. Whenever you query, it goes and identifies and gets you the data fast because the data is indexed. Similarly, here when you cluster the data, the entire data is sorted based on your clustering columns that you use, and then it becomes so whenever you go and then try to query from the table, then it becomes easy for snowflake to collocate that particular data. For example, you have some so there is a table called orders, and orders have order number, order header, order line, and then it has product, and then product number and product details, and then amount of the product, number of lines. So order, probably when we talk about order data, we are talking about lines, where for a particular order, for example, if you have ordered from Amazon, your order might have 10 items, your order might have 20 items, your order might have 50 items. And whenever you order something, right, internally what it happens, you are trying to buy a product, but the product can be divided into multiple things. They might be procuring from different places to sell you that order. Something like you are trying to buy a laptop, and the power card might be from a different place, or they might be giving you a backpack, and they have to, so your order will have the laptop, your power card, and then your backpack and everything. That is, so whenever you save your order, they're split into multiple lines. The lines have too much of data. Okay. And when I'm working in order management department, I am much more concerned about my order details, and then order number, order header, and all this stuff. When I'm looking from a finance perspective, I'm looking at a product and price of the product and all this stuff. So when I'm querying from the same lines table, order lines table, my wear conditions are different, and the finance people's wear conditions are different. So whenever you're querying, and if your table is deteriorating, that means the queries are taking a lot of time, and the table is in multi-terabyte range, then you can cluster the table. Cluster is like creating an index on the table, so that whenever you use the commonly used columns, like the order number, or header, or the line number, something, you would have already sorted based on it, so that whenever you query, it goes and gets you the data faster, because the ranges are already you. So that is what it has happened here. If you look at this, right?
Better than snowflake organized way, right?
Yeah, so better than the natural clustering. You are
Yeah,
now
natural.
trying to cluster the data based on your need. So if you look
Yeah.
at here, the data is organized by sold date, SK, and item. So the date and item is the one that they have identified. So whenever I query on this particular column, right, it gives me the best possible way. And if you query on the other columns, it might take some time. But these are the columns that normally used by my folks for reporting purposes, or the querying analytical purposes, or anything. This is the commonly used column. Or these columns might be used in the join conditions by the item when you are trying to join with. So you have to identify the best cluster key. I have a couple of pointers to identify what is the best cluster key, and then you can start it. So you are now trying to break the natural way of algorithm, natural clustering, and you are reorganizing the entire data based on your columns, so that you can get best performance out of it. This thing is called clustering. And initially it was, once you create a cluster, and you have to manually go and then recluster. That means if over a period of time, if the data has too many DML activity, you look at the clustering depth, and if it's not good, you go and then recluster the table. And alter table recluster is the command that you use, and it was a manual thing. And when you are trying to recluster, you cannot do any DML activity. So what Snowflake has come up with, auto clustering. Once you create a cluster, right? So then from then onwards, it's auto clustered. Whenever it thinks that the data needs to be clustered again, it goes and reorganizes the entire data in the table, and you can still do DML activity. So that is the advantage of auto clustering. Okay. So whenever the clustering can only be the your clustering, or your custom clustering, rather than the natural clustering, you always pick a table which is more than 10 terabytes of data, multi-terabyte range, more than. So depends upon how your queries are performing. So if you have data in terabyte range and your queries are performing bad, then you think of creating a cluster on it. So general indications that help determine whether to define a clustering key for a table. queries on the table are running slower than expected. I have noticeably degraded over time. The clustering of the table is large. Clustering depth is large. Then you think of clustering the table. So whenever you cluster, the data has to be reorganized. When you do clustering, all the micro partitions are marked for deletion and then reorganize the data, and then it creates new set of micro partitions. This is what happens. So this is the old data. It has alter table T1 cluster by so and so date and type, and then it was 1 2 3 4 micro partitions. Now it has created 4 micro partitions only, but you said date, right? All the dates are in order: 11 2 11 2 11 3 11 3. Here the dates are not in order. And then by type, the type is 2 2 2 3 3, and this is also order. Whenever you query something, and then it goes and identifies. So if you give this query, select name from where type is equal to 2 and date is equal to 11/2. How many partitions it has to scan in the upper before the natural clustering thing? Think this is a natural clustering as a regular table you have created and then insert the data. And if you issue this query where type is equal to 2 and date is equal to 11/2, how many micro partitions it has to scan? Type is equal to 2 and then date is equal to 11/2. How many micro partitions it has to scan? Guys, you have to answer me.
Sir, what was the question?
When I issue this query, select name,
Six.
country from T1, where type is equal to 2 and date is equal to 11/2, how many micro partitions it has scanned in the upper, this 4 one?
Three.
Four, four,
Three.
four are there. Type equal to
How
four
will,
are there, right? Four,
yeah.
four types, right?
So the 2 is existing in all the micro partitions.
All, yeah.
11/2 is only 3, but the type is equal to 2, right? It has scanned the other one as well. But the moment you recluster or cluster it, this is a natural way. And when you say take cluster by your keys, and you can have multiple keys in the cluster, not only one single column. You can have multiple columns in the cluster by condition. And now if you see in the bottom one, how many partitions it has to scan?
Only one. One, yeah, only one. Only
It
one,
has to
yeah,
scan
correct.
two, but
Two.
the second two will be scanned first, and then it omits the so. And if you look at this, right, the moment you create a micro partition, you recluster the table. The upper ones, 1 micro partition, 2 micro partition, 3 micro partition, 4, and here it's 5 6 7 8. It marks them. If you have, it keeps them for your time travel if you have time travel, or if you don't have time travel, it marks them for deletion, and it creates new names for the micro partitions. Because it's doing the clustering, the data is getting recreated again with a different set of micro partitions. You have to pay for the storage, and it takes a lot of compute power to do that, because we are talking about millions or billions of records. It takes a lot of compute power to do that. Then you have to pay for the compute charges as well as the storage charges. That is the side effect of doing a clustering. Are we clear? So this is an example alter table cluster by. When you
Because
cluster. Mhm.
one question here. Many are there many chances people go for explicit clustering, or it's better to go with natural clustering?
So clustering, normally people don't go that far. Why?
Okay.
So if the table
So
size is multi terabytes and the store says that we looked at is 1.9 terabytes, there they have created cluster. So it depends how you want to do it, right? If you have clustering also includes the compute as well as storage. You have to pay for both of them, right? It's not a easy thing. You have to. It's cost. It's not cost effective. So you have to be careful while trying to do it. and if your queries are very really bad and then it's taking a lot of time, then and your data is huge, then you think of going for a clustering.
Okay, thank you, sir.
Okay,
That,
and how do
that
you
happens.
decide?
Yeah,
Sorry.
that happens as long as the DML operations are happened, right?
Yeah, so
Yeah.
why would that means if your table depth is clustering depth is more, that means you have done too many DML operations and the table is not naturally clustered. The algorithm that they use now deteriorated because of too much DML activity.
Yeah.
Then the queries take a lot of time to get you the data.
Okay.
So how do you identify a clustering column? Mostly used in where classes. Add columns that are used in join predicates. I've already spoken, right? If you, this is the and then a large enough number of distinct values to enable effective pruning on the table. If you have large enough number of distinct values, it cannot be a primary key. So if when you have, then the range is much more. A small enough number of distinct values to allow Snowflake to effectively group rows in the same micropartition. So when you have large enough number of distinct values to enable effective pruning, if you have a distinct primary key kind of thing, then it has the range and it becomes easy for the Snowflake to identify and get you the data fast. And then if you have like um, states states in India, and then if you have data is segregated by states, right, you have only 25 states, and then the data is now when you look at the organization of micropartitions, right, and 25 states are organized properly and then they can effectively group. Okay, and if you have a column with two values, male, female, or yes or no kind of thing, that they yield minimal pruning. That means it has to 50% of the data has to be, and it's not an effective pruning method because 50% is still there. And a column with high cardinality is also not a good candidate for cluster keys. High cardinality means primary key is not a good candidate. If you have most number of duplicate distinct values, that is a so distinct having a primary key is not a better value for clustering, because high cardinal cluster is expensive to maintain. The moment you do an update and if you modify the particular primary key or something like that, right, it becomes difficult for Snowflake to maintain. So you remember column with high cardinality. High cardinality means more distinctness is not a good candidate, but a large enough number of distinct values. That means the distinct values are more in for a particular column, but all the data is not distinct, then that is a good candidate. So when you have high cardinality, means for example, if you have timestamp with milliseconds, and timestamp with millisecond is always a high cardinality because nanoseconds, the moment even if you do 100K records, the nanoseconds vary every second. There are about 100,000 nanoseconds for a second or something, right? I forgot the, and then each record will have a different nanosecond. The timestamp varies. So if you have that kind of scenario if you want to do a clustering, right, just use date. So dates, it pushes a lot of data, organizes a lot of data by date rather than timestamp. A truncate id comma 5, you can use a function in your clustering. You can use column or function of a column. Okay, and you have multiple columns to do the clustering. The order that you have to follow is, right, low cardinality to high cardinality. You identify low cardinality first and then the high cardinality, that is the order. So these are the ways that you can figure out the best clustering keys. Normally we go by the filter condition where that particular column is filtered, but and then you look at the low cardinality to high. When you are trying to create cluster keys, you use the low cardinality first and high cardinality. Low cardinality means more duplicates, high cardinality means less duplicates.
Yep. Sir, clustering based on gender is also not good approach, right? The
Not
fifth
good
point you
approach.
have mentioned.
Yeah, you have male and female. Yeah, it's not good approach
Mm.
because 50% of the data you might have chance 50% of data is can be so it you have to, and the other 50% you have to still scan, right? That is an expensive
Yeah,
operation.
yeah.
Okay. And whenever you're trying to recluster, why do you need a recluster? Too much DML action happening on a table, and you have to periodic. So by default now with all the clustering, whenever you create a cluster on a table, it's all auto clustering, and Snowflake identifies all this stuff and then reclusters whenever you need, and then you can still do the DML activity. And Snowflake maintains the whole thing. And this is what the clustering. So I've given an example. Okay, so let's do the so the first one there's a table which has P1, P2, P3, P4, P5, P6, and the query that I'm running is right. Select product, comma count star from events. It's an events table where event date is equal to 2/19/11/28, 2019/11/28 group by product. Okay, so this is something like you think the cities and then the table it has a date and cities. When you are trying to query for this particular table, when you issue the command where event date is equal to so and so, how does it affect how many partitions it has to scan? 2019 11 28.
Three partitions it has to scan, right?
Yeah,
First
P1,
three only.
P2, P3.
It,
And whenever say select same thing from the events where city is equal to Amsterdam, how many partitions it has to scan?
five, five,
P1, P2,
except
P3,
except
P4,
P5,
and then
P6 also,
P5.
P6
Yes.
also.
And when I say where city is equal to Dublin, how many partitions it has scan?
Only one,
Are you sure?
only one. Yeah.
Guys, here other folks are also following, right?
Sir, can you come
So
again, please, for the Amsterdam? Sir?
when you say where city is equal to Amsterdam, how many partitions it has to scan?
It is
Where,
5 partition, right?
yeah, 5 partitions. When you say it's Dublin, how many partitions it has to scan?
Can scan only 1 partition.
No, it has to scan 2 partitions because when you look at the range of this one, min and max is D only, Dublin. If you look at the P6 partition, the min is A and max is F. That means the Dublin might fall into A to F, right?
Okay.
It
Group name.
scans 2 partitions and prunes P6 and then it gets you the data for P5.
No, no, sir. Then A is there in P1, P2, P3 also, right? In that case,
Yeah, but we are querying for Dublin, right? Where is D? See, if you look at this P1, min is A, max is C. Min is A,
Mhm.
max is B. Min is A, max is B. Here min is A, max is C. Here no min, no max, it's all only D. Here min is A, max is F.
Oh,
Where
okay,
will
okay,
this D fall?
okay, okay. Based on min and max values. Okay,
Yeah.
then it will do.
So the data is not well clustered. When you go and reorganize all the A's and then B's and then C's and then D's, so you can get a better query from it. Okay. So I think we are out of time. So let's catch up in the evening for the remaining stuff. 9:55, right? So how many slides do we still have?
12.
30. Yeah, so this is done. So from 19. So yeah, so let's have a call in the afternoon, and then I think we can finish it, this micro partition. Look another thing. Okay.
Sure, sir. Thank you.
And is this session good or bad, or how do you feel? It's boring or
It's very good.
too much?
It's very
Very
good, sir.
interesting, sir.
Very good, sir.
Very, very
So now
interesting.
you can answer what is data pruning. You can answer what are micro partitions and all this stuff in detail, right?
Yes, yes, yes,
Yes.
yes.
Okay then, cool. Thank you guys. Let's catch up in the afternoon, 5 o'clock evening. Okay.
Yeah.
Thank you, sir.
Yeah. Thank you.